Very good morning to all of you. Uh, Thanks for joining from different places. I see we have faculty members and students from IIT Palakkad and from some other organizations. I would like to welcome you all again to the first talk in the HPC AI talk series, which is being organized by the IIT Goa HPC Nodal Center under NSM. So today we have with us Bharatkumar Sharma from NVIDIA. So Bharat has approximately 10 years of development and research experience in the domain of software architecture, distributed and parallel computing. He has also recently published a book on CUDA 10. He is currently working with NVIDIA as a GPU advocate. He has expertise in designing software for non-functional requirements and software migration to latest heterogeneous parallel architectures. Bharat has received his master's degree in information technology from IIT Bangalore. In addition to that, what I can say is that Bharat is also very active in organizing GPU hackathon and OpenACC hackathons and events in the country. And he has already organized quite a number of them, and many of them in association with C-DAC as well. So welcome Bharat to the talk, and thanks for agreeing to give this talk. So you can share your screen, and if you could share your video also, that would be great, but that's not a requirement. And and uh, and you can start. Over to you, Bharat.
Okay, I'm sharing the screen. There is some echo which is coming out. Just give me a second. Okay, why can't I share the whole screen? Okay, can you see the slides? Are you able
Yes,
to?
Bharat, we can see. Yes, yes.
And if I, is it in the presentation mode?
Yes, it is.
Okay. So thanks for inviting me, sir, for this series. I'm excited to talk in this forum. And the topic that we chose was to keep it kind of at a very, very higher level and a generic level to update the participants or to go through some of the, say, the overall evolution from our point of view in terms of heterogeneous computing. So, so first disclaimer, as we can see that in this world of COVID-19, we are all working from home, and in between, if we see some disconnection, please pardon me. I will definitely try to reconnect in between in case I get disconnected due to some power cuts. So, what's the agenda for my talk? We are going to talk about the need for speed, and that's something which will set the background or the foundation for why GPU computing is the new norm, or the accelerated computing is the new norm for both high performance computing and artificial intelligence. We'll go through some of the stacks and which kind of describes the new world of why it is not just about the hardware but the overall, I would say, the integration of hardware and software together and why it matters. Along with that, we will end with, we'll have some convergence of HPC and AI, which is the new, I would say, the most talked about topic, no matter which conference we go to. And this is a new thing which is being discussed. And finally, some of the items that I work on, which Sir mentioned some time back with respect to hackathons. So a very, very quick overview. I would try to be kind of making sure that we stick to the time. So I will go through some of this. If you feel that there is some topic which requires more addition, or if there is something which I have missed out on, we can definitely discuss this after the presentation as well. And in the end, obviously, this is just the beginning and we will collaborate more in the future. So just a perspective with respect to the system evolution itself, we started our journey of having mega flops based computation right? So mega flops, only we could do that many operations. And the architecture used to look more of sequential in nature, where there was a single CPU core attached to an memory. When we wanted to move from the megaflop era to the gigaflop era, we went from a single core CPU system to a multi-core CPU system, which evolved not just the your processor, which is say the Intel cards or any other processor that you buy, which is also called a shared memory processor. It not just changed the hardware, but also your programming approach. There were new programming approaches like pthreads, OpenMP, and Microsoft AMP, and you can name n number of them. All of them basically, so it was not just the hardware, but also the software which has to be changed to move from a mega flop to reaching this gigaflop era, right? And then we wanted to get more and more performance, and we went from the gigaflop era to the teraflop era. And for that, we could not achieve that within the same system. And that's why we connected multiple systems together using a high speed, high bandwidth, low latency networks like InfiniBand. And we were able to achieve that the teraflop amount of performance. But this also resulted into changes in your code, where you had to now start writing distributed programming approaches like MPI. MPI is the most common norm which is used for not just for the high performance computing applications like CFD or molecular dynamics, but also for AI world beneath the scenes. You see all the libraries basically making use of the MPI stack behind. So the reason for this slide is to show the bonding of how your hardware changes and how does it affect your application in terms of the software changes that are required to get more and more performance out of it. And then there was an interesting study which some of you might have seen, which was done by Stanford in 2017, which kind of said, and they kind of plot the so by something called as Moore's law, which I will come to in the next slide as well. But it kind of said that there were fundamental innovations which was changing the hardware, and the software industry kind of stopped. And then there were innovations which were happening on the other side to get more performance in the CPU world, which is also called a general purpose processors. Was with respect to say having more instruction level parallelism or better branch predictions and things like that. But they were not something which was like fundamental change in the overall design, which could get you more performance, otherwise which would have resulted into which used to be there in the earlier days, which we were talking about. So instead of showing you this graph, maybe let me show you this one. So this is a plot which was done as part of the study, and you can see what you see here is uh, your axis here is basically the performance, and what you see here, you can see it's 10, 10x, 100x, 1000x, and what you see here is your timeline of here. So you could see that if I were to say that if my application was sequential and if my processor was changed, single core processor was changed, if I was getting 10x in 1986 or 1987, and then I could reach 100x by 1992, right, for the same, which basically fundamentally meant that I could get 52% performance gain by changing the processor and doing those changes into the processor and the compiler stack year on year. But it kind of changed after 2002, and you can see that change of getting more performance for your application went down from 52% to 23%, and now it stands almost at 3.5% per year. So what does it mean? Basically is that there was a fundamental shift which was required for your applications to get more performance, and what that was something which we'll look into some time, which is also called as accelerated computing, or also called as GPU computing. But what does the new scientific computing actually mean when there are supercomputers which are built? The supercomputers are not just built for one purpose. They are general purpose processors, which means that they may have a component of your traditional simulations of CFD, molecular dynamics, astrophysics. There will be some applications which are going to make use of visualization, because your data is quite huge, so you basically would like it to be visualized as well. You would also have a component of AI there, which also talks about um, maybe typical AI patterns of deep learning, or it may be the convergence of HPC and AI, where you are making use of deep learning techniques or machine learning techniques into your and fitting it into your traditional simulation. So you can see the new scientific computing talks about different parameters, and some of the supercomputers do have a plugin to themselves where they can deploy, say, whatever they have done into the cloud in case they wanted to scale it as well, right? So if you see the new definition of scientific computing, it includes workloads from simulation, visualization, AI. If you are doing big data work, it also includes data analytics, and also there might be a necessity of putting it into the cloud. So that's what is the new scientific computing is all about. And there was a evolution which happened because of multiple reasons that all of you know, but AI kind of has its presence in almost all the fields that we talk about at this time, including the traditional simulations for weather or CFD or molecular dynamics or whatever you would like to name. And the approach, if I were to summarize in very simple, was that in the earlier days there was a programmer who used to write this logic, say sorting logic or whatever logic, on a input data, and then the computer used to process that and then push out the output data. What changed was that this amount of data, which kind of drastically increased over time, and it was almost impossible to write logic for almost all the different combinations which were possible. Like if I was doing autonomous driving car, it's almost impossible for me to write each and every scenarios there with respect to a bike being ridden, or maybe following the path versus say reading the signals, red, green, blue, in the weather conditions of rainy, not rainy, and all, right? So it became almost impossible to do that. And the new approach, which was it is not a new approach, but it is something which has become really evident and useful in new day in this date, is because of the availability of lot of this data. And we will talk about it with respect to high performance computing also soon. Was that you just replace this over time, you have generated so much of input data, you have processed it, and you have the output data. What the new way of machine learning says is that you have input data, output data, and let me throw out the logic for you. So that was another way of approach in terms of changing on how the evolution of programming also happened from the traditional side to evolving to applying AI or machine learning to some of these I would say topics which are relevant, and I will cover that to certain extent later on as well. So for I told you that we need all this, we need more and more performance, but why is the question, right? So just to give you an example, this is a study which was done in 2017 again, and it kind of shows what you can see here is that you have small data region, and then you also have the irreducible error region where you cannot reduce the error any further. And the more and more training data was provided, the better and better you basically went into the region where you started getting more and more accuracy. So it was proven that more the data is fed in, the more accuracy is expected, and lesser error is expected in your algorithms, right? But what did it mean for compute also was that it is also proven again that the more data you increase, it was directly proportional to increasing your model size as well, which resulted into from a few tens layers to now even hundreds of layers is a very common norm in terms of artificial intelligence, which finally resulted into more and more compute requirements to process so much of data. So you got more data, which resulted into increase in the size of your model, which then finally resulted into ask for more and more compute. And that's where accelerated computing plays a very, very important role. To show you some numbers, where I said with respect to the Moore's law, was that Moore's law was directly proportional to the number of transistors, and it says that every 18 months the number of transistors doubles, which is also kind of related to the performance. If the transistors double, basically it also results into more performance. So it kind of was like every 18 months you get twice the amount of performance by changing the processor architecture, which we saw earlier for the CPU world, it kind of also flattened out. But if you see from a GPU perspective, what you are seeing here is our simulation softwares or our high performance computing software stacks from different world, even from WASP to Quantum Espresso to NAMD to GROMAX and Amber, different kinds of applications. And you can see that over time, this is our architecture called as Pascal, released in 2016. We had Volta card, which was released in 2018, and our latest architecture is called as A100, which is Ampere architecture. And you can see the jumps in terms of performance, and these are all jumps in performance with respect to the application themselves and not theoretical performance. And you can see that GPU also goes beyond Moore's law. You can see from here to here, if you were to go from V100 to A100 within 1 year's time, and not even 18 months actually, you get from 4x to 9x performance gain within 1 year, right? And why is this even possible at this point of time? We'll cover that topic. And that's why we say that GPU computing goes well beyond Moore's law, which is also quite evident in the case of, so what I showed you in the previous slide was the high performance computing world, and this is more in terms of the AI. And if you see here, you can see the difference and the demand of the compute which is there. On the right hand side, you can see because of using the high performance computing stack of GPU in the AI world, it's basically doubling every 3.4 months, not even 1 year, not even 18 months, but it kind of doubles every 3.4 months, right? And this is what we are calling it as beyond Moore's law, or Moore's law square, as somebody would like to call it, as some of the analysts also use this term. But that's the requirement at this time, that there is more compute required. And when I say compute, it is not from the point of view of theoretical performance. Generally, the tenders and everything come out in terms of the theoretical performance, which is one criteria. But what I am talking about here is not the theoretical performance, but the application performance itself. I showed it to you for high performance computing. The same I am showing it to you for making use of high performance computing for the AI world as well. And it has taken us 25 years to reach this. We have invested a lot, not just into our hardware, where we keep on increasing the theoretical performance, but as I said, there is a tight coupling between the hardware and the software stack, and we take a lot of pride in it, right? Because hardware, there is a very interesting study which I have not quoted here, which kind of said that if you don't change your software stack, you are basically not utilizing your hardware in the most efficient manner, and then you will be bound to only the theoretical performance provided by the processor architecture vendors out there. And that's why it has taken us 25 years to reach here, which is also called as our CUDA stack, Compute Unified Device Architecture stack, where we changed things starting from the operating system, drivers, compilers, libraries, communication frameworks like MPI, to moving on to the application and then creating some domain specific ecosystem around there. Over time, we also evolved it from a single CPU, single GPU system to now you will see that 4 GPU, 8 GPU or 16 GPU systems are very common, because it just didn't it was not just about one GPU, but it's all about the whole system, and finally all about the whole data center. And you can see the whole system consists of not just a GPU, it consists of an interconnect between the GPU. It also consists of how does the CPU basically talk to the GPU, how does the GPU talk to your interconnect like NIC, right? So that's where we invested a lot, and I will come to that part as well later on. And that's why you see these kinds of performance which goes beyond Moore's law, which is not about hardware theoretical performance. And this has been all possible because of our CUDA stack. And you can see CUDA has become the most downloaded accelerated computing programming model out there, and almost all more than 700 plus applications in this high performance computing world make use of CUDA in different way to use it. So what is accelerated computing all about? from the beginning, we made sure that GPU does not do all the work. There is no silver bullet. GPUs cannot run an operating system. We said we'll create an architecture which is very, very good at doing parallel computing, which is very common across different, if you see workloads. If you would already know NVIDIA is very good at graphics and gaming. And if you see what is graphics or gaming is that you are basically rendering and painting pixels on the screen. And if you see every pixel is independent of each other and it can paint the red, green and blue on the 1024 by 1024 image. If you see graphics itself was a parallel computing workload or a high performance computing workload, which we took as the first challenge, moved on to the high performance computing, where we could also make use of this parallel architecture for say fast Fourier transforms or doing other things like convolutions and all. And today we also accelerate AI as we speak in terms of say machine learning algorithms as well. But as we said, we are very good at doing parallel computing, and that's our motto. We leave other things which CPU is very good at, like running an operating system or multitasking jobs, which is fundamentally a multitasking job where you launch multiple say applications and it can switch between those applications very, very efficiently. So you have your application which has both these parts. Some of the part remains on the CPU, some of the part gets offloaded onto the GPU, and GPU can run that part very efficiently. Also known as 80-20 principle, where we say that in your application, 80% of your time is spent in 20% of your code, which is primarily your for loops. And that is the part which GPU can accelerate very well, because it basically, as you can see, it has large number of simple cores which can do these operations in parallel. Like Volta card has around 5120 cores. You can practically work on 5120 elements at the same time, unlike your CPU. So this combination of CPU taking the workload which is latency based, while GPU taking the workload which is more throughput based or parallel, makes this overall combination run best, and that is what is called as accelerated computing. And GPU is not a alternative to CPU at all. They actually work together to make sure that your overall application, which has both these combinations, actually runs much faster, which can be defined by another law also called as Amdahl's law, because I can't just accelerate one part and give you more performance. It needs better to work on both the parts. And that is what GPUs from the beginning, starting from your graphics to high performance computing to artificial intelligence, it's able to solve that parallel computing task, which is inherently part of all these workloads. So as I said, CUDA basically is a slave which serves multiple masters, right? Which has this parallel computing or high performance computing needs, from your traditional scientific computing like computational fluid dynamics, astrophysics, to data analytics or big data, to AI training, also visualization, machine learning. There's a new upcoming field of 5G networks, and you would have seen that the amount of computation required for 5G networks is enormous. And that's where also it plays a very, very important role to cloud gaming side as well. So CUDA as a slave serves all these masters, and it has a huge breadth of platforms. And that's why the software stack, I said that we invested. If you see NVIDIA has, we have 40% of our employees are in India, and majority of them are software engineers. So we have the ratio of software engineers dominating the hardware engineers, because most of our efforts, a lot of it actually goes in maintaining this software stack, from driver to compiler to even application. And I'm going to give you a glimpse of it in my coming slides. But what are the pillars which we talk about? First one is our architecture itself, which is the CUDA architecture, which is something which is changed this industry in terms of how do you write parallel codes. So as I said, that you also need a very high speed interconnect to make sure, because none application can run only on a single GPU or say on a single core. It needs to talk to each other. And finally, the stack itself. To just show you an example, this is our latest architecture A100. It has different features inside it, If you are in this molecular dynamics field and you are doing FP32 based thing, then you can actually get a peak of 312 teraflops. If you are in this field of AI inferencing, you can actually get up to 1 petaflop of performance. If you are in this field of high performance computing CFD where you use 64-bit precision, you can get up to 20 teraflop of performance as well, which is, you can see from our previous generation, which we released 2 years back, it is almost 20 times, 20 times and 2.5x more and speed up as compared to our own architecture. I am not even comparing it with other architectures here. So it goes much more than beyond the Moore's law, and it's one of the largest single transistor which has been kept because it has almost 54 billion transistors inside it. What does it result into? As I said, I have given you multiple examples from NAMD to physics to engineering to geoscience. Fun3D is a code basically from NASA, and it is also used heavily for computational fluid dynamics. And you can see from Volta to Ampere itself, you saw performances in the range of 1.5x to 2x, which is well beyond Moore's law thing, right? But it's not just about that. Let's take example of something else as well. What if your data, or if you need sparsity, right? Not every data is dense. Some of it is sparse. So in our architecture, we did include something called as tensor cores, which makes use of the sparse matrices, and it tries to exploit the sparsity in your code, and it basically provides you much more better performance if you make use of this sparse nature. So if you know that your data is sparse and you tag it with the sparsity, it will run on a specialized core which can give you more performance than your traditional general purpose code that you would have written, which doesn't take care of this sparsity. Or sometimes it so happens that GPU is such a powerful architecture that sometimes we get this request that my one application cannot make use of GPU completely. What we have come out is something called as multi-instance GPU, which means that my GPU can now be broken down, or it can be partitioned into 7 different instances, like a virtualized instances, where you can run multiple smaller workloads on the same GPU, which does not share the resources on the GPU. So think of it like virtualization in the hardware itself, so that your GPU gets much more efficiently utilized in your data center or in your supercomputer, because maybe only just one application cannot use the whole GPU, because GPU is such a massive card and it gives you so much of performance. Maybe one application cannot. So why not that multiple applications can make use of the same GPU? Maybe one user is running Amber or a CFD application, and the other guy is running a AI inferencing, and the third guy is basically running a TensorFlow operation. And that is possible with hardware-based partitioning, which we have introduced, which is also called as multi-instance GPU, where you can actually partition the GPU. Now, these are the architectural level changes that we keep on doing in our architecture year on year. And this also gets shown into our software stack as well, which I will come to in the later slides. But what about, say, the performance, right? So this is one example of an indigenous code, and this is like one of the code which is also which we can say very proudly from India is also at the level of exascale at this point of time. This is a code from JNCSR. We work with JNCSR, Professor Rodham Narasimha, and also Deshpande sir from JNCSR. You can see it's a CFD code. It's based on DNS, and you can see the number of GPUs basically it's able to consume, and it can scale linearly from 25 GPUs to also till 200 number of GPUs for 250 million cells, and it can still scale more. It's not that it can stop. Why we stopped here was because of the number of GPUs which were available for JNCSR to run on at that particular point of time, right? Why is it possible? Because as I said, we have changed our software stack, and the second thing is we have evolved the network, something called as NVLink, which provides you very, very high bandwidth and low latency when you do this communication across GPU and also across nodes. So this is an example, Indian example, that we have worked with JNCSR, and within the same system, if you are talking about deep learning, the same thing applies. This is an example here again. As I said, NVLink can. There have been some apprehension with respect to the number of GPUs per system. You can see this is like 16 GPU per system, and still it can scale very much linearly for the ResNet network, and it still give you, and you can see the throughput is in terms of images per second, right? So if you are running 1 GPU, you get around 1000 images per second. With 4 GPU, you have almost got like 3000 images per second. For 8 GPU, it's almost 6000 images per second, and for 16, it's almost touching 13,000 images per second. And that's possible because of our software stack and also the network topology, which is the NVLink based topology, which was earlier not possible. Now coming to the most important part, which is our software stack itself. And you can see that first of all, NVIDIA, there is no software that NVIDIA sells. All our software stack is free for use. You can go download it anytime you want. Like in terms of high performance computing, we have the whole software stack, which is named as HPC SDK. You can see it consists of compilers, different libraries, starting from matrix operation to CFD based solvers, to tensor operations, to sparse matrices, fast Fourier transforms, random operations, to communication libraries, which is included in all the OpenMPI stacks or MPH, to even for communication libraries for deep learning, to different programming models. You would have seen that the programming models are getting integrated inside the language itself. Like C++17 has support for GPU programming inside the language itself. Fortran has support for GPU programming inside the language itself. That's also coming out. There are easier methods to write GPU programming. It used to be hard to write GPU programming, but today we have directive-based approaches like OpenMP and OpenACC, which target GPUs without you getting to know how to write parallel code, because compiler can generate parallel code for you. If you want to get best performance, you write lower code. If you want to have okay performance and you want to basically just concentrate on domain, you can make use of OpenMP or ACC, or you can make use of standard languages like C++ and Fortran without getting to even stick to a particular hardware format. And also there are profilers, debuggers, and everything that we publish is all available in our GPU cloud, which is also called as NVIDIA GPU cloud, which I will come to later on as well. When it comes to the AI stack, it's the same story. In AI world, it's kind of understood that if you are using TensorFlow, if you are using PyTorch, if you are using machine learning, all this are basically accelerated behind the scenes. We have a whole set of army of engineers who work with TensorFlow developers, who work with PyTorch developers to make sure that the GPU is integrated in form of libraries into all this, where you have to just call one API that use GPU, and the overall pipeline will basically end up running on the GPU. And it is all available no matter which framework you talk, whether it is cloud or in your own systems as well. But if you see from a breakdown perspective, if I were to break, deep learning is still very small subset of your artificial intelligence, and traditional is still machine learning, and analytics still plays a very, very big role. So you have your dense data, and then you have your tabular sparse data as well, right? And deep learning is primarily very good in working on dense data like images, video, and voice. So that's how the workload is across, and the good part is that we don't need to reinvent the wheel, and majority of this software stack is already present. Like if you're working in the space of machine learning, and if you are making use of pandas, or if you are making use of scikit-learn, there's already a library which is called as rapids, which is already out there, and instead of calling a CPU call, you just end up calling a GPU call, and it is already out there as an open source project on GitHub, and it's not something which is proprietary as well. You can contribute to it in the future. So it's an open source community out there, and it is being used not just by the researchers but also by enterprise softwares like SAP, Oracle, and all startups, and also there's a lot of integration which happens in the rapid side. If you are working in the space of the artificial intelligence or using AI for healthcare, we have a software stack which is called as Clara. Now, if you look at the typical pipeline of a healthcare industry, the first would be to label the patient data. So we'll make use of AI assisted annotations, and then you will make use of things like transfer learning. You will output a model, and then finally you will deploy it. Now, the good thing is you don't need to start from scratch. We don't expect anybody who's using GPUs to start from scratch. So there is something called as NVIDIA Clara. As you can see, it runs on any GPUs, but it has various components inside it, including the libraries, different containers, and it has basically different kinds of models which have already been trained on different aspects like tumor segmentations and all. It also solves a very critical problem of anybody working in this world where data is the biggest problem. We keep on hearing that data is not available. What should I do? That person or the hospital is not ready to share the data. There's this new concept, or it has been there for quite some time, which is called as federated learning, where the user, end user, or the say the customer like the hospital does not need to give you the data. What you are going to do is you're going to give him your model. He is going to train that, and what you get back is your trained model only. So this problem of sharing the data goes away with this concept called as federated learning. It's a very simple concept, but if you are able to use it using one API or two API using a framework, why not? It kind of solves your problem so that you can concentrate on your own work rather than doing anything else. And we have created these workflows for CT, MRI, ultrasound. If you are working in this space, this other space of multi-model conversational AI, right? There is a framework or a SDK which is called as Jarvis, which does exactly the same thing, where we have created all these pre-trained models for you. If you want, you can retrain them using the transfer learning, but it basically helps you in multi-model. When I say multi-model, what it means is that your data can be voice, your data can be also audio, it can be other streams of continuous data. Now you are going to use speech, vision, NLU, all of that, and you need to finally combine them to finally result into something which is like an environment called as multi-speaker transcription. Like if somebody is speaking, I need to move my camera towards that guy and make use of AI. Now all this is finally possible using the whole stack called as Jarvis, right? We don't expect anyone, and the best thing about it is that we don't expect you to start and train everything. What we have done is we have trained one of the all the latest models out there for many weeks on our supercomputer which NVIDIA has, and kept all those pre-trained models for you so that you can additionally use transfer learning and just retrain it rather than starting and running it from the beginning, which may take you days or weeks or months also to train, right? If you are in this other space as well, if you are in the recommender system, where it used to take few days and now reduced to few minutes, and this software stack is called as NVIDIA Merlin, and it has these components for recommender system. You can see the whole integration. I don't have enough time to go through this, but what main point I'm trying to say here is that the whole stack is basically kind of available for you. You can go ahead and download it, and that's where NVIDIA believes in the tight coupling of the hardware and software, so that you don't get into this space of starting from scratch. And all of this stack that we talk about is all loaded as a store or a cloud, which is called as NVIDIA GPU cloud, in form of containers. So you can any day go there and pull those containers on your own system, or you can pull those containers on any of the cloud vendors like Amazon or say Google Cloud or anywhere, and run it in form of containers rather than installing all the software stacks on your system, right? And that's what all the things that I talked about, whether it is the highly efficient implementation of GROMACS, NAMD, or CFD codes, or AI deep learning, or the trained models that I'm talking about, everything is in form of app store, which is also called as NVIDIA GPU cloud. You can anytime pull those containers and run it on your system without getting to do a lot of installations on your system, on your premise, all on a and the same container can be pushed to the cloud or to a hybrid cloud or also to the edge in case you are working on the inferencing side of it. And that's the new norm, and we have tried. I will show you on the browser later on if anybody has any queries where you can go to and look at this NVIDIA GPU cloud and make use of all the optimized accelerated stack rather than starting from scratch, right? And generally there are these questions. I'm not a salesperson or anyone, but I'm more of a technical CUDA programmer. But in every call I usually get these queries, and that's why I'm just bringing it out to you. We have different kinds of solutions which are available there. The desktop cards are called as Titan or GeForce card. The workstation series that we have is called a DGX station, which has 4 GPUs inside it. And also if you are in the data center or supercomputing environment, these guys are called as Tesla cards. And you will get them from any of the server platforms, from HP, from Dell, for anyone you name. But the NVIDIA system is called as DGX, which has 8 GPUs inside, or you can also get up to 16 GPUs per system. So if you have a card which is called a Titan or GeForce, it is a desktop card, while the same code can actually run in a workstation or a server environment also. So the container that I talked about, it can run on your gaming card, it can also run on your professional card, on your data center, it can also run in a cloud environment. The same container can run everywhere. And the naming conventions, as I said, V stands for Volta, which was our earlier card. A stands for Ampere, which is our latest generation cards. T stands for Turing. So that's how our naming conventions are. And everything which has 100 is the most fastest card that we have. So if you have anything which is with 100, means it's the highest end card in that particular architecture. Because we keep on getting this question, that's why I just thought of bringing out, but no details there. But I would like to quickly go into this field of HPC and AI convergence, also called as using AI for science. Now, this is something which is emerging. We see a lot of supercomputers making use of these workloads, and the fundamental concept is very simple. All our simulations are mathematical models, and they are based on first principles, but there is some level of approximation we do to when we write our codes, because computers cannot exactly represent all the floating point operations, right? So you basically have an input, you define some mathematical models, and that's your output. But while writing the codes, you will approximate it based on the algorithms and your computer limitations, and that's your real input and the output that you get, right? But as you said, you are anyhow end up doing this approximation, right? What if this approximation can be actually done with help of say a neural network? That's the question which this emerging field is trying to solve. And if I were to say create a particular theorem around it, the answer theoretically is yes, and it is proven by something called as universal approximation theorem, which you all might know, which kind of is very simple, and it says that any contiguous signal basically can be represented, can be approximated using neurons inside a artificial neural network. That's what this theorem actually proves, but it is practically a useless theorem unless it is being worked upon and also proven for more detail, or I would say the kind of signals or the kind of contiguous signals that you have in the real world. So theoretically, yes, it can be done, but whether it is useful is something which is the new research field which everybody is talking about. And bringing back to the previous topic which I said, what we are saying is that, as I told you earlier, if you look at deep neural network, what it does is that it takes your output, it takes your input and throws out the logic. So over time in the high performance computing world via simulations, you have basically created so much of output, which is the collection of tag data for you, right? So it's like you already have your input, you already have an output which is mathematically or first principle proven. And what I'm going to do is basically train my network using this output data and see if my network can actually do the same operations which we were doing traditionally in a typical simulation environment, right? So if you see, we have more information about the ground truth because our simulations already have output so much of simulation data. And as we said, the good the data is, the better your neural networks can perform. So sometimes it may feel as disadvantage, but actually it's a really, really good advantage, and that's where we are trying to work on. And there are gaps which are getting filled at this point of time, starting from somebody is working on adversarial fuzzing or tools based support, which can be considered as art, which is just like I give an input data, yes, it gives me the output, but I don't know why. Or the extreme end where there are physics informed networks or ODE networks, which basically also takes in an angle and trying to define these networks in form of physics principles. And that's where NVIDIA has a software stack which is called as also SimNet, which is basically exactly this, which is more of a network which is physics informed, and we are trying to also create a curriculum around it. We are working with IIT Bombay on this, and soon you will see that the whole curriculum will be out on this part as well. So as I said, so all models are wrong, but some are really useful. We are almost in the end, very near, but I would like to quickly just go through how NVIDIA collaborates in terms of different aspects. I am particularly responsible for a couple of them. NVITC stands for NVIDIA AI Technology Center. Don't get baffled by the name AI. It consists of everything related to GPU computing. It may be related to writing a CFD code of the next generation, or it may be related to coming out with a new network, or it may be related to convergence of HPC and AI. And I'm driving this initiative in India, which is called as NVIDIA AI Technology Center. It's a it's a research collaboration between the institute and NVIDIA, where we work together with the professors who have a student along with a research problem statement, and we dedicate our engineers, we put in more resources from our side and make sure that that research actually is gets accelerated, and also it has a industry collaboration angle with the institute. And if you look at NVITC, it's a global project with NVIDIA has in different parts, and we had our first NVITC in India at IIT Hyderabad, which is a collaboration with the Telangana government. So Telangana government and also IIT Hyderabad, and we also have NVIDIA in this, and we are working on the projects which are relevant to agriculture and also the smart city projects in this. So in India, we have one center, but you can see it's a global collaboration. Researchers in India work with researchers in Taiwan. They work with researchers in Indonesia as well. So it's a global research collaboration which we try to form as part of this NVITC. And if anybody in this forum is interested in getting to know more about NVITC, I will be happy to talk about it after this, or also you could shoot out a mail to me. Also, with collaboration with C-DAC and National Supercomputing Mission, we try to conduct these hackathons, HPC hackathons and AI hackathon. The next one is in September. You can see that in the 2018, we started our journey. We had all these different applications coming from researchers from different institutes, almost all the IITs in these domains. This is not a competition. This is more of like you bring in your application, we bring in experts who are parallel computing experts. We sit together and accelerate your application to get more performance. These are some of the numbers, like as compared to a 24 core Xeon Gold, the application got like 30x performance. So like you can think like instead of taking 30 hours, now it took only 1 hour within a span of 5 days. So this is like in 5 days, it's a very, very methodical manner in which we can do. And also you can scale your code in case it is already GPU accelerated as well, right? Same thing we did in 2019. We got more number of applications, and you can see IISc, NCRA, IPR, and BITS Pilani, and all those different IITs participated in this. We got almost 470 times speed up there, and the average speed up was almost 80 times in our next one. We also conduct AI hackathons. AI hackathons are more of competitions, and we do it with the government. You can see it was with the government. It was related to COVID-19, and so that's our one way of another way of also collaborating with the institutes and also with the with the government of India. Now, with that, I think I will stop. I've been continuously talking for almost 45 minutes now. Uh, the first question that I will have is, am I still audible? And Professor Sharad,
Yes, Bharat, you were audible all the time.
okay. So I hope it gave a very a higher level overview in terms of the overall stack. I hope it was as per the expectations of the 45 minutes we had. And I'm open to more questions now if you'd like to start.
Sure. So we can take questions from our participants. I already have one question, so maybe we'll start with that first.
Mhm.
So Nidhan had one question: is MIG available on V100?
MIG is not available on V100. MIG is a feature of only Ampere card. But said that MIG basically is a hardware-based partitioning, right? But you can still partition your GPU, which is software-based, using our software stack called as Grid. So you can still do that, but it will be a software-based partitioning, while MIG is a specific hardware-based partitioning, which is only there in Ampere.
Okay. Then he also has a follow-up question, which is, do you have some open source applications or tools in the lines of NVIDIA, Clara, Parabricks, genomics pipeline that can be run on a GPU server with V100? He is looking for a GPU-aware version of the popular sequence aligner BWA.
Okay, so there have been some efforts in terms of BWA, but as you would have seen that our approach, we acquired this company called as Parabricks. And our approach towards providing a solution is via Parabricks. Parabricks is not open source, but it is something which we at the time of the pandemic of COVID-19, you would have seen that we made Parabricks free to use. So you can very well go ahead and approach the Parabricks team, and they should be able to provide you the free version of the Parabricks. While there are other initiatives of a BWA algorithm, but NVIDIA in general doesn't have a solution which is kind of like open source at this point of time. But just to give you a history, like we acquired a company called as PGI. PGI had a solution in terms of OpenACC based compilers and all. And after we acquired the company, after 1 year or so, we made the compiler free of use. So that's what has been the method of NVIDIA. So you might see something coming in the future. But from NVIDIA side, currently, yes, you can contact Parabricks and you can get this software for free for your BWA algorithm. And Clara is anyhow free. So you can anytime go ahead and download Clara. It's all there in the container. You can anytime go ahead and download it. And by the way, if you are in this field of this space, you should look at this new initiative, which is called as Monai. Monai is a new initiative which I can show you if you would like to see. Let me see if I can share my browser again. I hope you are able to see the screen. So
Yes,
Monai,
it's
Monai is
visible.
is a new initiative where NVIDIA is quite involved, and it stands for Medical Open Network for AI. And we are creating a lot of training material around this. So you should definitely go and also try to see if there is anything that you are looking for. It's all present on the GitHub again. You can go ahead and look at Project Monai. It's the most followed field in this healthcare environment, and it's based on also PyTorch. Are there any more questions? I know it's exactly 12, which was the duration, but
It's so any other guest, if you have any question, please type in the chat box. Uh, okay, in the meantime, Bharat, I have one question. or rather a couple of questions. First question is, you see, typically when we create an HPC, we create an HPC infrastructure at an the HPC facility is CPU heavy, and I would say only a few nodes are GPU oriented. So, do you see a possibility of HPC infrastructure being more balanced in terms of CPU and GPU, or GPUs being more in number compared to CPUs?
So if you look at the top 500 supercomputers list, actually is the ratio is opposite. So every system has like 4 GPU or 8 GPU inside them. If you look at Summit supercomputer, all the fastest supercomputer except for the one which is there in Japan, all of them are powered by a system of GPU, NVIDIA GPU, and they all have minimum 4 GPUs per system, which means a ratio of 1:2. One CPU has actually 2 GPUs. And the reason why this is possible, or this was possible, was because of the know-how of the workload itself, which means that there was a when we look at this from their point of view, it was very simple. When the Titan supercomputer, Summit supercomputer was developed, it was said that okay, I have these applications which is called as GROMACS, NAMD, Fun 3D, this, that, everything, and I want to get the best performance out of it. Can you basically project what kind of a performance numbers I can get for different architectures? Obviously, GPU showed much more better performance on the benchmarks which were given by them. And once those benchmarks were shown that they performed really well, they went with a completely GPU centric. It's actually accelerated centric workload rather than CPU centric workload, because it basically is 1:2 ratio, right? So the first thing whenever a data center is built is to understand the workload of, like, say my workload is 10% GROMACS, 40% is a CFD application called as OpenFOAM, 10% is basically say AI based application, and once that workload is known, it becomes very easy to come out with a say that okay, how many GPUs or how many CPUs should go into my system, right? I would say that's the approach. And if you see the worldwide supercomputers, that's how they are. In India, unfortunately, we don't have it except for one system, which is Anurag, which is the defense system, which is completely GPU, as in the whole system was basically 1:1 ratio, which means one CPU has one GPU. While the NSM systems currently, if you see the way they have been developed, is that they have 30% of GPUs, right, currently. But there is a provision to increase it to 20% more, which makes it 50%, 50% workload after, if we make sure that there is enough workload on the GPU, which means that if an institute who has a GPU based system and they basically have overloaded the GPUs with respect to AI workloads or any other workloads, then it's very easy to ask for more GPUs, and there is a provision which is given as part of the National Supercomputing Mission, keeping into this aspect that more and more workloads are going to be GPU centric or accelerated computing centric. So that's how even India is going. We have not reached there, I would say. There are few systems like TIFR system, or there is a system from IPR, which is in Ahmedabad and all, which is like completely GPU based system. But the main thing I'm trying to say here is it's all based on workload analysis. And all my slides you would have seen were not theoretical performance at all. So if there's a proper workload analysis, then the ratio can be defined for the supercomputers, upcoming supercomputers as well.
So just a quick follow-up question on that. You see, normally when educational institutions purchase or want to establish HPC infrastructure, they go through this tendering mode where they have to spell out the specification of the system. Now, do you think, based on what you said about workload characterization, educational institutions only say the workload looks like this, okay, and leave it to the vendors to propose a solution, then that would be a better approach in terms of getting the maximum.
Yeah, because finally, see, why does the institute need a supercomputer? to make sure that the researchers are able to do more research, right? So if the institute basically floats a tender telling that I want this much minimum performance for my GROMACS workload, this is the benchmark, then every vendor will basically make sure that they basically provide you a solution where the time of the researcher is saved. And that's the intention of your high performance computing software, right? If the institute floats a tender telling that, okay, I want a theoretical performance of 1 petaflop, it doesn't mean anything. It's obviously one of the criterias for you to finally say that 1 petaflop has been reached for the vendor to showcase you, right? It definitely is one of the most important criteria also, but there should be enough weightage also given. Points in your tendering system should also be given to the applications themselves, right? So think of it from NVIDIA side, right? What my role is to make sure that your applications runs the best on the GPUs. So if you float a tender which says that GROMACS should run with this much, I'm going to make sure that I incorporate inside GROMACS a GPU computing element or work with your researcher to make sure it gets the best performance on that, right? So it's a win-win situation for both the vendor as well as for the institute. And there are various examples like that. In fact, I can send some of the tenders, and in fact most of the tenders are like that I have seen in across the world. Is like it says that from when I go from this supercomputer to that supercomputer, GROMACS should have improved by 2x within the same power budget. Power budget is also very important because uh, buying a system is less costly as compared to maintaining it. So they say 2x the performance of GROMACS within this power budget. That's it. So it's a very, very clear demarcation for anybody now to go back for any vendor and then give you a solution which is best for you, and you get it verified in that terms.
Okay, thanks, Bharat. So Nidhan has one more question, which is
So
I think
so
okay,
A
somebody, yeah, go ahead.
A100. So the question is A100 available for order in the India now. So A100 is currently available not as a separate GPU, but it is available as part of our DGX system, not as a separate card, but it will soon be available. So in case you are looking for a DGX based system, yes, it is. Yeah, the answer is yes. But from OEM perspective, it will soon be available. And A100 comes with SXM and PCI. You are right. So the SXM module is 400 watts and the PCI module is 250 watts. That's the correct thing, Nidan.
Okay, so yes, maybe we take one more question if anybody has any question. Okay, so in that case, when I share, a talk like this with the students, they see that there are a lot of libraries, there are a lot of different ways of looking at the CPU of the software stack and hardware stack. There are just too many things for them to comprehend, easily. Now, if I ask a very basic question that if say somebody wants to see acceleration, where do they start? What are the baby steps that they should take, to get started and then explore the.
Okay. So if somebody wants to learn CUDA or how to accelerate, say, HPC simulations, or say somebody wants to know how to make use of say Clara or Jarvis or anything like that, or if they want to learn parallel programming, we do conduct in collaboration with National Supercomputing Mission something called as boot camps and hackathons, right? So the best way to learn is that to learn on the own applications, correct? So what we do is we conduct a 2 day or 1 day boot camp where it's completely hands-on, and we start from the most basics of how to what is parallel computing to writing a efficient CUDA code using different approaches like compiler based to lower level code during that time. And we have a series of these lectures which we keep on doing with National Supercomputing Mission. This year, because of COVID-19, we were able to do only online ones, but it's like you can think of them like every month or so we do conduct these boot camps. So the students can basically come and learn in these boot camps, but our final goal is that they learn on the application themselves. So they should definitely participate with their own applications in these hackathons, or if they would like to compete in the AI hackathon, they can participate there. So boot camps and hackathons, I would say, would be the right. And I believe the Ashish sir and all of them, they keep on sending to all the NSM sites the invitation for the boot camps which we do. So if anybody is interested, they can anytime. It happens every monthly as well. And if there is any research problem statement that they would like to work with us in close collaboration as an industry partner, as I said, we have something called as NVITC. So if any of the professor or the institute is actually interested in having a research collaboration with NVIDIA, we can take it forward in terms of defining it formally in form of NVIDIA AI Technology Center. And as I said, it's for HPC, it's for AI, it's basically for accelerated computing, and it can be any research topic which is of interest for the institute. So these are the two ways I would say would be the best way from our side in terms of learning it. And recently I also did a for NPTEL. Basically there are some lectures of mine in case the student wants to go through, and I can share the link to you later on as well. They are on the NPTEL portal in terms of what GPU computing is, how they can write code, and also they can also go through those lectures as well. So I would say that these are the three approaches which could come to my mind as the first three things.
Okay, I think that answers. So I think, okay, so Nidhan has a message that from NIBMG, they will reach out to you on genomics research collaboration.
Thanks. We're definitely looking forward to it, Nidan. I don't know. So later on, I believe that sir will anyhow send you this slide or recording along with
Yes,
the email ID as well.
yes. So I think so for the guests here, I am Dr. Sharad Sinha. I'm a professor in computer science and engineering at IIT Goa. So if you need, in case I miss out sending an email or video recording, please feel free to drop me an email. My email ID I'll give you in the chat box here. So with this, let me thank Bharat for a very nice talk. It was very nicely organized, and I think our guests and participants got an overview of accelerated computing using HPC and targeting AI. We already have a response from NIBMG. So thanks once again, Bharat. I will share this video. I have taken your consent for recording, so I'll share this on our YouTube channel as well, on IIT Goa YouTube channel. And we'll also share through other social media platforms. And we would definitely, very well, we would be interested in working together.
Yes, looking forward to that, sir.
So yes. So thanks again, Bharat, with this, and thanks to all the guests from different institutions who joined. Thanks for coming. With this, we'll end this talk, and all of you have a good day. Thank you, everyone.